Hello everyone. Today we are going to discuss one of the important topic from class 11 mathematics, probability. But before that, we'll know some basic terms and definitions first. First is random experiment. An experiment whose outcomes cannot be predicted or determined in advance is called a random experiment. It will be very clear if we see an example here. Tossing of a coin, rolling a die, drawing a card from a well shuffled pack of playing cards, etc. These are some examples of random experiment, as because we cannot predict while tossing a coin whether head is coming or tail, like that. After that, we'll know about sample space. It is the set of all possible outcomes of a random experiment. It is denoted by capital letter S, and the number of element is n s. As for example, in throwing a die, the number that appears at top to any one of 1, 2, 3, 4, 5, 6. So here S is the set comprising the elements 1, 2, 3, 4, 5, 6, and number of elements in S is 6. After that, we will define event. It is defined as every subset of a sample space is an event. It is denoted by capital letter E. For example, in throwing a die, sample space is the set comprising elements 1, 2, 3, 4, 5 and 6. Now if you define the event such that event E is the appearance of an even number, will be the event E comprising element 2, 4, 6. Obviously E is a subset of S. After that, we'll come to know about simple event. An event consisting of only one sample point is called as simple event. As for example, if you throw a die, you will get ashes, the set containing 1, 2, 3, 4, 5, 6. So each of the singleton set containing elements 1, 2, 3, 4, 5 or 6, they are examples of simple events. After that, compound event. An event which has more than one simple point is called a compound event. As for example, if you throw a die, the event of appearing an even number is a compound event, as because E is the set containing elements 2, 4, 6, which has 3 elements, that is more than one element, so it is compound event. Then we will come to know about equally likely outcomes. All outcomes with equal probability is known as equally likely outcomes. The definition will be clear if we see one example. When a coin is tossed, both the two faces, head or tail, they are equally likely outcome. Then sure event. Let S be a sample space. If E is equal to S, then E is called a sure event. As for example, if you throw a die, S is the set containing element 1, 2, 3, 4, 5, 6, and let E be the event of getting a number less than 7. So E is a sure event, as because number of elements in E equal to number of element is S. Then we'll come to know about mutually exclusive or disjoint event. Event A and B are mutually exclusive event if their intersection is a null set. Example, when a coin is tossed, the event of occurrence of a head and the event of occurrence of a tail, they are mutually exclusive event. Then we will come to know independent or mutually independent event. Two or more events are said to be independent if occurrence or non-occurrence of any of them does not affect the probability of occurrence or non-occurrence of the other. Means occurrence of one event does not affect the occurrence of other event, then this kind of event is known to be independent event. Then exhaustive and mutually exclusive event. Let S be the sample space associated with a random experiment E. Set of events E1, E2, En are said to be a set of mutually exclusive and exhaustive events if their union is the sample space and the intersection, just Ei intersection Ej is equal to phi for I is not equal to j. Then we'll know about complement of an event. Let S be the sample space for random experiment and E be an event, then complement of E is denoted by E dash. Here E dash occurs if and only if E does not occur. After that we will come to know about classical probability. Let there be an exhaustive, mutually exclusive and equally likely cases. Out of them, let M be favorable to the happening of an event A. Then the probability of occurrence of event A, denoted by PA, is defined as PA, number of favorable cases divided by number of exhaustive cases, is equal to Na by Ns is equal to M by N. Then we'll come to know about axiomatic approach to probability. Let S be the sample space of a random experiment. The probability P is a real valued function whose domain is Ps, that is power set of S, and range is the interval 0, 1. So as to satisfy the following axioms. First axiom is, for any event probability of E is greater than equals to 0. Axiom 2, probability of sample space is equal to 1. Axiom 3, when E and F are disjoint event, then probability of E union F equals to P plus Pf. Now we'll describe probability of an event. If there are n elementary events associated with a random experiment and m of them are favorable to an event A, then the probability of occurrence of A is defined as Pa m by n. The odds in favor of occurrence of the event A are defined by m is to n minus m. The odds against the occurrence of A are defined by n minus m is to m. Now we'll discuss some important theorems on probability. First one, in a random experiment, if S be the sample space and A an event, then probability of A is a non-zero quantity and probability of null set equal to 0 and probability of S equal to 1. Then theorem number 2, if A and B are mutually exclusive event, then probability of A intersection B equals to phi. Then we'll come to know theorem 3, if A and B are two mutually exclusive events, then probability of A plus probability of B equals to 1. Theorem number 4, if A and B are mutually exclusive events, then probability of A union B is equal to probability of A plus probability of B. Theorem number 5, for any two events A and B, probability of A minus B equals to probability A minus probability of A intersection B. Theorem 6, addition law, for any two events A and B, probability of A union B equals to probability A plus probability B minus probability of A intersection B. Now theorem 7, addition law for three events. If A, B, C be three events associated with a random experiment, then probability of A union B union C equals to PA plus PB plus PC minus P of A intersection B minus P of B intersection C minus P of A intersection C plus P of A intersection B intersection C. Corollary, if A, B, C are mutually exclusive events, then probability of A intersection B is equals to probability of B intersection C is equal to probability of A intersection C is equal to probability of A intersection B intersection C is equals to 0. And probability of A union B union C is equal to PA plus PB plus PC. Then theorem 8. For each event A, probability of A bar equals to 1 minus PA, where A bar is the complement of any event. Then theorem 9, if A and B be two events such that A is a subset of B, then probability of A is less than equal to probability of B. Finally, theorem 10, if A is an event associated with a random experiment, then probability of A lies between 0 and 1. Thank you, children.